Okay, so this is the problem again, copied on the left corner. We're looking for a solution in the form of this series. Let's get ready to differentiate with respect to t, x, and then plug it in here. So partial t, we gotta be very careful on how to take these derivatives before we plug them in into the PDE. So partial t, that doesn't affect sine of nx, so that's going to be summation of bn prime of t sine of nx. Again, bn is not known, so that's just bn prime of t. Let's do partial x twice directly. So that doesn't affect bn of t. And just to make it clear, let's put it in the corner here, right? So if I differentiate sine once, I get n cosine of nx. If I differentiate it again, I get minus n squared sine of nx. Okay, so uxx will be bn of t, and put here minus n squared sine of nx because of the chain rule. Furthermore, and that's another essential step to keep in mind, at this point, any coefficient of the part that depends on t, even if it's a constant, by the way, even if it's 1 times e to the t, that 1, or whatever the coefficient is, needs to be written in terms of the same Fourier series. So you have to look at the coefficients, I mean, to the table of Fourier series, and replace that coefficient with the appropriate sine series. So if I look at the table, you can look at the table over here in the book. We have pi minus x, and you can see why I chose this example, because it's a nice compact series, right? And you can bring this 2 inside the summation if you like, so that you won't lose it. Okay, so pi minus x is the summation from 1 to infinity, 2 over n sine of nx. And plug these guys into the PDE. Okay, so let's just do that. And let me see, let's do it here from the left side of the paper. So u partial t on the left side is going to be summation of bn prime of t sine of nx. uxx, let's put this minus out, so summation from 1 to infinity minus n squared bn of t sine of nx, and pi minus x e to the t, so we can start with e to the t, and instead of pi minus x, write its corresponding series, 2 over n sine of nx. Again, go very slow. There's no point to rush. Make sure you understand every single step. Okay, so if you look carefully, what we end up with is a giant equality of 2 summations in sine of nx. And we can simply identify the coefficients of sines left and right. Let's do one more intermediate step, although later on you can skip it if you understand what goes on. So I'm going to basically group all the terms on the left, on the right-hand side in a single summation, just to make it clear. So if we combine these summations and pull out sine of nx, you're going to be left with minus n squared bn of t plus 2 over n e to the t. That is the key method of why this thing works. Okay, because you will end up with a mean to find the appropriate Bn of t. You basically obtain, if you match these coefficients, you obtain a first order ODE in Bn of t. And this is the step when you need that first order ODE to solve it. So let's write down the ODE. So what is that ODE? Well, Bn prime of t should be equal to minus n squared Bn of t plus 2 over n e to the t. Now we have to go back and carefully look at the boundary conditions. All right. So remember, we are looking for a solution in this form. I want you to see carefully that the homogeneous boundary conditions are satisfied no matter what Bn of t is. Okay. So when I plug in 0 for x, so u of 0 t, sine of 0 is 0, sine of n pi is 0. So these guys are already satisfied. They don't give us any new information about Bn of t. On the other hand, u of x0 equals x will give us information about Bn of 0. So when you plug in 0 for t in the initial condition, so let's just do it here. So u of x0, that's going to be summation from 1 to infinity. Oops, it's out of range. So u of x0, summation from 1 to infinity, Bn of 0, sine of nx. Again, this step sometimes is subtle and people miss it or misunderstand it. By plugging in this summation into the PDE, we get the ODE that gives us Bn of t. By plugging in that summation, that format, into the initial condition, that gives us, or will give us, some information about Bn of 0. So u of x0 is equal to this, which is equal to x as the problem mentions. So what is Bn of 0? Well, obviously, I need to get now x in terms of a series, in terms of sine of x, sine of nx, which is stuff you do already. If you remember, this is always what you do at the end in the process of solving boundary value problems by separation of variables, right? At the very end, the initial condition is written in terms of a Fourier series. So again, we go back to the table and we see that x is given by this series, 2 minus 1 to the n plus 1 over n sine of nx. We write it down here. So 2 minus 1 to the n plus 1 over n sine of nx. And now we match Bn of 0 with the coefficient of that summation. So Bn of 0 equals 2 minus 1 to the n plus 1 over n. Okay, the problem is not done. We have to move on and find Bn. Again, this is the nature of the beast. I hope by this point you became patient. This class is really exercise in patience, because the problems are long and we really have to focus on what we do one step at a time. I know that I say this quite often and it might be even annoying at this point, but in my experience, there is always difficulty in this class with students used to quick examples that essentially test the same skill over and over again. So it's a lot of repetition, so to speak. There is repetition here as well, but problems are more focused on, they are more comprehensive essentially. And each step has its own meaning and you just can't zoom through it, without understanding what you're doing at each point. Because if you do, you will miss something important in the logical flow and you'll become very, very frustrated because you will not understand what you're doing at a given point, and that's the worst feeling probably when you learn math, to be frustrated. So follow my advice to the letter. Go slow. So going back to the problem, let's review where we are right now. Okay, so we took a solution in that form. By plugging in the solution everywhere in the problem, we arrive to basically an initial value problem that will give us Bn of t. So we have an ODE in Bn of t, a linear ODE. We have an initial condition for Bn of 0. We just have to solve this linear ODE. So at this point, we have math to 70, or ordinary differential equation problem. And after that, we're basically done. So on the second page, I'm not going to make another part to keep the flow. On the second page, let's do just that. Let's copy again the ODE in Bn prime of t. And at this point, you can drop off t, because obviously it depends on t. We don't have to specify it all the time. And because it's a linear ODE, let's write it in the standard form, which is suitable for the formula that I gave you in the first part of the lecture. So in the standard form, Bn prime, so the Bn's, the dependent variable, should be on the left side, so plus n squared Bn equals 2 over n e to the t, and Bn of 0, 2 minus 1 to the n plus 1 over n. So t is the variable of integration, n is going to be a constant. So constants are not really difficult to handle, but it makes a little bit of a tedious work if you think about it, right? I mean, this is just a number, but it depends on n, and you just have to carry these terms, minus 1 to the n plus 1, whatever they may appear. Other than that, actually, this is not really a difficult problem. And it's very similar if you look back to the first example that I did in this lecture. So according to the formula that I provided, I1, the first integral, is the antiderivative of n squared dt. So that's n squared t. And I2 is the integral of b of t. I mean, like, what I mean is the right-hand side, okay? So 2 over n e to the t times e to the I1, which is e to the n squared t dt. And we need to combine those exponentials. So e to the n squared plus 1 t. This is sort of like integrating e to the 5t if you want, right? It's e to the 5t over 5. So it's just a u substitution for this exponent. So the antiderivative will be 2 over n, 1 over n squared plus 1, e to the n squared plus 1t. And Bn of t, according to the formula, again, you should write that formula separately so you can see it in front of you. It's e to the minus I1 c plus I2 now distribute this exponential and we could simplify it, e to the minus n squared, so minus n squared t plus n squared t plus t. That just leaves it as e to the t. Finally, we need to deal with the initial condition for Bn in order to find the constant of integration c. Okay, so Bn of 0 on one hand is c to the 0 plus 2 over n times n squared plus 1 e to the t. And that ought to be 2 minus 1 to the n plus 1 over n, right, from the initial condition. Finally, that gives me c 2 minus 1 to the n plus 1 over n minus 2, I'm sorry, So Bn of 0, that's e to the 0, which is also 1. So 2 minus 1 to the n plus 1 over n, minus 2 over n squared plus 1. We're going to leave it like that. We don't have to simplify it further. So let's just state what Bn of t is. Bn of t is C, which is this guy, e to the minus n squared t, plus 2 over n times n squared plus 1 e to the t. So we're practically done. Hard to believe, but we're done. We just need to write the whole solution put together. Okay, so once we find Bn of t, we can plug it back into the full solution. So our solution was what? A summation of Bn of t, which we just finally determined, 2 minus 1 to the n plus 1 over n and this guy, and then times sine of nx. Okay, I hope it was as good for you as it was for me. So we're going to have another part in which I want to illustrate the main steps of the method. Because again, once you understand the main steps, it should feel easier. And I want to be very careful when I mention this. When I say easier, I don't mean not tedious and not long, but easier in the sense that the main steps should be pretty familiar to you. Because it's important when we go over other examples to actually skip some steps and focus on some of them that are newish, essentially. Because if we do every single problem from top to finish, we're going to take more than a lecture for a single problem, and that's not practical. So once again, at this point, you shouldn't have a problem understanding how you go from the PDE to the separated form and the Sturm-Liouville problem, okay, for this example at least. So when I say this equation leads to this Sturm-Liouville problem, it should be pretty straightforward for you to actually do the steps or take it for granted, that those are the eigenvalues and function and so on. Because other examples are variation of this. So for instance, if the boundary conditions were derivatives like Newman conditions, well, I mean, pretty much it's the same, except that you will probably look for cosine series. And we're going to have actually, in my next lecture, I want to move on with a new topic. I'll just go over examples of the involving the techniques we learned so far. So, like I said, one last part to give some guidelines of the method, and then that will be it for today.